Welcome back to Frank Stajano Explains and to the first year algorithms course at the University of Cambridge. Any book on algorithms will spend quite some time on the fundamental problem of sorting. You have a multi-set of elements and you want to rearrange them according to the order defined on them by some comparison relation. For example, who is tallest, who is oldest, who is heaviest, who has the most cash in their wallet right now, and so on. As you know from the discrete mathematics course, an order is a relation that is antisymmetric and transitive, and a total order is an order that is defined for all pairs of elements. And in this course, for simplicity of demonstration, I am usually going to sort integers, but the algorithms generalize trivially to sorting any other items, provided that the total order is defined on them. And you've seen in the object-oriented programming course last term how you can pass a specialized comparison function to a sorting routine, which might also let you do fancy things such as sorting by surname but breaking ties based on first name and then breaking further ties based on date of birth and so on. Now in this course we largely ignore the comparison function and we instead concentrate on the inner workings of that sorting routine. Before we write any code or even pseudocode, let's get into some good computer science habits. I need an array of cells to hold the things that I am sorting. Each position is numbered. Ordinary people start counting from 1, like this in blue. 1, 2, 3, 4, 5, 6, 7. But computer scientists use the natural numbers, and so start counting from 0, like this in green. 0, 1, 2, 3, 4, 5, 6. Counting from 0 is much better because then the base plus offset calculations that are so common in computing work out fine. For example, imagine that I place this array inside a bigger array, such as inside the memory of my computer, which is where all my data lies, and you may view the memory of the computer as one large enormous array of bytes, each with its own address. So I place our array at position 1000. What's the position of the fourth element? Well, in the array it's item number 3 in the zero-base counting, and in memory it's at position 1003, which is nicely 1000 plus 3 equals 1003, base plus offset, easy peasy. If I use the stupid blue method of counting from 1, this would be element number 4 in the array, but it's annoying that in memory it's still at position 1003, not the 1004, and this leads to off by 1 errors. So a good computer scientist will always start counting from 0 as opposed to 1. The reason ordinary people count from 1 is because by the time they finish counting, then the last number tells them how many items they counted. So 1, 2, 3, 4, 5, 6, 7, I counted 7 items. Whereas if you count from 0, 0, 1, 2, 3, 4, 5, 6, you didn't count 6 items, you counted 7 items. And that is slightly annoying. So let me show you a trick. When you index the cells of your array, don't put the index under the cell as we've done here, but put the index on the left boundary of the cell, like this. So this is index 0 and this is cell 0, and this is index 1 and this is cell 1, and so forth. And the last boundary here is 7, which is not the index of any cell, but is the number of cells in the array, even if I started the count at 0, because obviously there is one more boundary than there are cells in the array. So I get the same benefit as the ordinary people do, with the added advantage that my base plus offset calculations work. And another advantage of this notational convention of putting the indices on the boundaries as opposed to put them under the cells that they refer to, is that you can easily compute the size of a range, such as the one I highlighted here in red, by subtracting the indices of the boundaries. So here 5 minus 2 is 3, and there are 3 cells between these two boundaries, which is great. It's Otherwise, if you look at the indices under the cells instead of the indices on the boundaries, it's easy to look at the range from cell 3 to cell 5, and then you get an off by 1 error because 5 minus 3 is 2 instead of the 3 cells that you have. So these little tricks, counting from 0 and indexing at the boundaries, are the mark of the smart computer scientists. I'm going to write some numbers in my array. 8, 7, 2, 4, 10, 3. Okay. So the first sorting algorithm I'm going to speak about is called insertion sort, insert sort. And it's the algorithm that is used by people who play cards when they receive the cards from the dealer. Dealer gives me a card, I put it in my hand. Give me another card, I put it in my hand. Give me another card. And the property I maintain is that I keep cards sorted in my hand, and when I receive a new card, I put it where it should be to keep the whole thing sorted. So I always have my cards in hand sorted. The next card comes in, I stick it in the middle and sort it. So if I had a hand here, I would receive these cards from the dealer. I receive 8, I put it in my hand. It's already sorted because there's only one. I use 7, and I would have to put it before the 8. And I receive 2, I put it before the 7. And I receive the 4, I have to put it between the 2 and the 7. Now, if I do these things with an array, sorting the array, I can model by saying, I'm going to have an index here that what did I call this index in here? I. So this index points at the part of the array that contains the cards I've already received. And as I move this index around, it means I'm expanding the part of the array that contains things I've seen. So initially, it's here because I haven't received anything. If the first thing I receive in double quotes from the dealer is 8, then I move this here to say this region of the array is the one contains things in my hand. And this region here is the things that I haven't been dealt yet. So when I'm given the 7, then this is the region that contains the things in my hand. But the 7, I've just received it. I need to put it in order. So the trouble with the array is that I cannot put the 7 where it should be because it's already space for this. So I have to also move this around. When I receive the 2, I cannot put it where it should be. I have to also move things around. And what I'm doing now is a bit of a cheat. That's not how it works in a program. In a program, all I can do is assignments. So in a program, what I should be doing is, okay, I'm receiving this 4, and what I do is I can put it anywhere. I should just make an assignment. And what I can do is I can check if it should be to the right or the left of this other number next to it. And it says, well, actually, it should go further this way. And then what I need to do is to copy this somewhere that won't be overwritten, some temporary variable, copy this in a place where the 4 was, and then put the 4 in here. And then I should check again against this one. And he says, yes, it should really move. So again, copy this here and put this there. And then I check it against this one. And now finally, it's greater than this one, so it can stay where it was. And then I move this further, and I check. This one that comes in, how does it compare to this one? This time it's bigger, so I don't need to move it. I can just move around and say, well, it came in at the end, and it should have been at the end, so I leave it there. And in here, if I receive this 3, then I have to check it against this 10. And yes, actually, I do have to swap those two. I have to check it against this 8. Please close the door. And it has to move, so it has to keep moving until it reaches its natural position over there. So this is the algorithm known as Insertsort. This algorithm, which is in your handout on page 18 in pseudocode, like this. So this pseudocode is kind of pretend computer code, but I can get away with writing natural language when I need to. Define a function called Insertsort that takes some input A, and here in lighter ink I write a comment which explains what this function does. So I have 3 things that I explain about this. One is behavior. What does it do? Run the Insertsort algorithm, which we've explained, on the integer array A, sorting it in place. So this is in the context of a thing that explains how Insertsort works, and it's a well-known thing. I don't have to explain it any further in here, but otherwise, in a generic program, you would give details on what actually your routine does. And interesting here, I have a precondition and a postcondition. A precondition is what I require from my caller when this function is invoked. The array A contains length of A integer values. Well, that's not a very demanding precondition. Interestingly, it's one that I didn't meet because there was no value in here. This was an array of size 7, and it did not contain a 7th element. So I have not met this precondition. And the postcondition is array A contains the same integer values as before, but now they are sorted in ascending order. So this is a view of programming as an activity that involves a contract between 2 entities, the one that writes the routine and offers a service, and the one that calls the routine and makes use of the service. So the person who builds the routine and maybe even sells the routine says, I will do my work provided you give me this precondition. If you call me having satisfied the precondition, I promise on my honor, I will exit and satisfy the postcondition for you. So if you call me and you've satisfied the precondition, on exit, I will give you back the postcondition satisfied, or you can get your money back. You can sue me, okay? It's my job to satisfy the postcondition, but only if you've satisfied the precondition when you call me. If you call me and you haven't satisfied the precondition, then all bets are off. I can do anything I like, I can format your hard disk, and it's your problem. So you see this contract. Everyone has responsibilities and obligations and then rights that come from these. It's an instructive view of the business of programming. So I urge you to think of what the preconditions and postconditions of your own routines would be as you write them. So I have a for loop for I from 1 included to length of A excluded. So my I, there's no point starting here. I start here because when I have one item, it's already sorted, so might as well. Going all the way to length of A excluded, this one. And I say the first I positions are already sorted. This is an assertion. in many modern programming languages, you can even have the assertion not as a comment, but as a statement that you can insert in the code. And this will translate to something that at runtime checks the Boolean predicate you put in. And if it is correct, then everybody is happy and the program continues. And if it is incorrect, then the program stops and sounds a siren alarm. Beep, 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 beep. My assertion is violated. You probably have a problem that you hadn't anticipated, because you said that at this point this was always true. And in this case, it's not true. So you have a problem. You have a bug. And you can also, if you are reckless, at some point invoke your runtime with the assertions disabled, so they won't be checked. But in the hope that you may go faster. But it is futile to go faster if you are giving incorrect results. You just give incorrect results faster. So it is a good idea to give correct results, and the assertions will help you give correct results. So it's a powerful technique to have an assertion within each loop that says, this is true every time I enter the loop. So every time I enter the loop, it is true that the things that are to the left of I have already been sorted. Okay, and then I do the stuff, I do the swaps. I have another loop inside here. You might wish to consider putting an assertion inside the smaller loop, and so on. These assertions might help you build a proof that your program is correct. For example, you say, if whenever I come into this loop, the first I positions are already sorted, and I can persuade myself that the body of the loop adds one more position to the sorted ones. So now the next position is also, I'm extended by one, just like I did before, is also making a longer sorted initial substring, left substring of the array. Then when I enter again, I has increased by 1, and it is again true that the first I positions are sorted. So if I come in and it's true, then the next round is true, provided I can prove just a smaller thing, that this body extends the sorted region by 1 position. And if I start by checking that this assertion is verified the first time I go in, so at the beginning, when I is equal to 1, the first is sorted. Yes, it's sorted because there's only 1. It cannot be out of order. Then I have guaranteed that this happens when it exits. And since what I wanted on exit was to have the whole array sorted, and I've reached the end, then this helps me build a proof that the algorithm sorts the items it was given in the array to begin with. So that's on a very trivial example, but that's a technique that generalizes. The next thing we are concerned with after correctness is cost. So how much does Insertsort cost to run? And you could imagine costing each of the instructions in here. You have to make some assumptions about how much it costs to run one instruction. Is it the case that all instructions take the same time to execute? Well, no. You have to somehow make things even. And if one of these instructions is actually a call to a function that contains many more instructions, then obviously it's going to take longer than a simple instruction such as this assignment. Even this assignment is not just an assignment. It's first executing some arithmetic operation, then assigning the value here, which would take longer than just j equals 3, for example. But you cannot follow all the detail to the extreme, otherwise you never finish, you never get anything done. So provided that you are not calling other routines, for example, swap, actually it means doing 3 assignments. Copy this to a temporary place, swap this and this means copy this somewhere, copy this there, and copy this there. So this line here means 3 assignments. I have to abstract away from a number of details, and although in theory, what I'm doing is I'm basically taking the view of the microprocessor and saying how many instructions does the microprocessor see as this program is executed and unwound. So the for says, well, repeat this instruction many times. And the microprocessor sees these instructions many times. How many times? Well, a number of times that is variable depending on the size of the array. And so I want to say, how much does it cost for a size of array n? And as I vary n, how does the cost vary? If the array is 10 times as big, does it take 10 times as long? Or does it take more than 10 times? Sometimes it doesn't grow proportionally to the input size. In fact, I'd be very happy if it grew proportionally to the input size, but it grows faster than proportionally to the input size. And how much faster? So that's the type of things I want. I don't really care the exact time. I don't want a formula that says, given n, the exact number of instructions is big complex formula. I don't care. I just want to know the rate of growth. And so if the complex formula is, for example, a polynomial, all I care is the degree of the polynomial. I don't care about lower grade terms because the highest degree term is dominant over them. And as I move n more and more towards larger values, it will always dominate the lower terms regardless of the coefficients in front. So I ignore the lower terms, I ignore the coefficients, and I just say this grows linearly, or this grows quadratically, or this grows cubically, or other things like that. So if you make your programs twice as fast, you don't get any medals in this asymptotic complexity view, because if your program was quadratic, then twice as fast is still quadratic. It's just a coefficient in front, which I said I ignore. Even if you made it 10 times as fast, you wouldn't get any credit in asymptotic complexity terms. Of course, you would get credit if you're working for Google. They'd probably give you a promotion. But if we are looking at asymptotic complexity, the only thing that matters is if you change something that was of complexity n to the fourth and you make it n to the third, then that's something that is worth writing home about.